Okay, so now we're going to look at our vectors in physics. And we're going to break this. I'm going to break this into two videos. One is just some basic vectors and math of vectors, and then we'll break it down into unit vectors and how physics uses vectors for in the subject. Okay, so the first thing, right? What is a vector? So a vector is a quantity that has both magnitude and direction. So it has to have a size, right? And it has to have a direction. That's what separates it from a scalar quantity. So this is really a complete description, right? So at times a scalar tends to be incomplete because it doesn't give you this direction piece. So easy way to represent it is pictorial as an arrow, right? Where the length of the arrow shows the magnitude. So like this size here would give you the magnitude, okay, or the size, and then the arrowhead points in the direction, right? So this, whichever way it's pointing, will be the direction. And sometimes what you will also see for direction is actually an angle down here. Okay, so sometimes you may see it written as a magnitude and an angle. Okay, other two key points with a vector. Okay, this end here is called the tail, and the tip of the arrowhead is what we call the tip. Okay, that's going to be important you'll see later when we add and subtract. We're going to place them tip to tail. So what we mean is we're going to take the tip of the first one, place it to the tail of the second one. All right. Now, oftentimes you see vectors written in book, they're going to be written as boldface, but we're going to be doing a lot of this work on worksheets and paper. So if you have to handwrite a variable that is a vector, you're just going to place a variable over or an arrow over the variable. So for example, acceleration. Okay, that little symbol there, that's our vector symbol. Velocity. Okay, and these are the three that we've talked about, right? So acceleration, acceleration, velocity, and displacement. And then we're going to come to here shortly is force. So this little symbol up top, that is our vector symbol. Okay, that means that particular variable is a vector, which means we have to include the direction. So you do got to pay attention to what the problems are asking. Like if it just says what is the speed, you don't have to worry about the direction. But if it says what is the velocity, this would be the symbol you use. Plus, you'd have to include the direction. Okay. Now the next area here is what happens when we have to add or subtract them graphically. So graphically just means by picture, right? Not necessarily involving the numbers unless it's done on a graph. Then you can see how what the components are and so forth. But mostly just overall in picture form. Okay, so one way to add vectors is to do so graphically. So what you're going to do is you're going to place the tip of the first and put it to the tail of the second. Okay, so sometimes you'll hear me say tip to tail. Okay, so that's how we add them. So we're going to place the tip of the first to the tail of the second. Okay, now the resultant, which is just simply the answer, okay, is the arrow drawn from the tail of the first to the tip of the second. So the process to add is tip to tail, but the answer is tail to tip. Okay, so just like when you're adding numbers, vectors follow the commutative property, which means order doesn't matter, right? So if I'm adding vector A to vector B, I will get the same answer if I added vector B to vector A. So if I do that as a picture, right? So here's A. Oh, I wrote a B instead of actually drawing vector B. Right? So if I have vector A plus vector B, right? Place them tip to tail. So here's A, here's B, right? Here's my tip to tail, right? My answer now is from tail to tip. So the tail of A to the tip of B. So here's A, here's B, here is my answer, which is resultant R. So this is A plus B. Now let's say we did B plus A. All right, so we're going to do B plus A. So we're going to do B plus A. Okay. Now this isn't going to be exact science, right? If I had drawn out nicely, right? So we're going to place the tip of B onto the tail of A, and then here's our resultant. All right, so there's R. So this is B, this is A, and this is R. And again, if I had drawn this nice and neatly, right, this R would be the same size as that R, because remember, adding follows the commutative property. Okay. Now subtraction is going to be just a little bit different. Okay. So we can subtract. The easy way is to subtract them graphically. Okay. But the goal of subtracting is to turn it into addition. Okay. And I forgot, this should be by finding the inverse, or sometimes we'll say the negative, of the second vector. Right. So if I'm subtracting A minus B, I want to turn this into A plus negative B. Okay, so if I have my same vectors, here's A. I'm going to do A minus B, right? So what I'm going to really turn this into is A, sorry, like my letters. So I'm going to do this A plus negative B. Okay, so I'm going to flip B, right? And now I can add it graphically. So I'm going to do, let me move this. So here's A. I'm going to add negative B, and now here's my R, right? So this is A, this is negative B, and this is now R, okay? But you have to remember, when you subtract, vector A minus vector B does not equal vector B minus vector A, okay? So if you want to just kind of quickly look at what does that look like as a picture. So if I did B minus A, so here's B, right? I'll subtract A. So what am I going to do? I'm going to do B plus negative A. Right? Now I can draw my tip to tail. So I'm going to take the tail, or the tip of B, place it to the tail of A, or in this case, negative A. Right? And so now here is my resultant. Oh, not negative R, it's just R. Right? Because that's our answer. So you can see that these two are not equal, right? In fact, they're inverses of each other, right? So these do not equal each other, okay? So vector A minus vector B does not equal vector B minus vector A, okay? Now, most of the time in physics, though, we're not going to look at the pictures, right? It's one thing you may have to do, but what we're going to do is we're going to add them algebraically, right? So we're going to use the numbers. That's what algebraic means, right? So we're going to use the numbers to solve these problems, okay? So when adding and subtracting algebraically, the first thing you need to do is resolve, or sometimes you'll see it called decompose, okay, the vectors, so all vectors really, into components. Now, when it comes down to the end, you're going to have two components. You're going to have an x component, and you're going to have a y component, okay? So to do this, you're just going to use simple trig. Okay, what's the simple trig? It's just going to be sine and cosine. Okay. So if I have vector A, and I need to do this algebraically, okay, I'm going to break this down into two pieces. I'm going to break it down into an x piece and a y piece. So I'm going to have ax, ay, right? And then this is my angle. All right, and you can see easily this is the adjacent side. That's why we use cosine. This is the opposite side. That's why we use sine. All right. So now once you got all the vectors broken down into components, right, you're going to do this for ax, ay, bx, by, however many vectors you have. You're just now going to simply add the horizontal pieces, right, or the x pieces, and the vertical pieces, right? So you're going to treat them, now you're going to treat it, separately. Okay, so you're going to add the horizontal components, add the vertical components. Now, when you do this addition or subtraction, right, it's going to give you the horizontal and vertical components of that resultant. Okay, so after this step, right, and again, this would be based on your numbers, I have my pieces, right, so I have Rx and Ry. And then you move into the final step, which is now to find the magnitude and direction, right, of the resultant. Now, how do we do that? So the magnitude of the resultant is basically the hypotenuse of that right triangle I just drew, right? So it's this piece, right, of the triangle, okay? So this is now R. So you're trying to find what I just wrote in red here, the magnitude and the direction of the resultant, okay? So the magnitude is just simply the hypotenuse of the triangle. So how do we find that mathematically? Well, we use good old Pythagoras, right? Pythagorean theorem. So we're going to say Rx squared, or the square root of Rx squared plus Ry squared, right? So we're just going to use Pythagoras. Right? A squared plus B squared equals C squared, where this is now C, right? And the direction just can be found by using simple trig. So I have the opposite and adjacent sides. Well, that's the tangent. But I'm not looking for the ratio, I'm looking for the actual angle. So I'm just going to do the inverse tangent of our opposite over adjacent, which just breaks down to be our y value divided by our x value. Okay, our y divided by our x. And I do want to make sure we point out that this has to be in degrees. So make sure your calculator is in degrees. All right, if you get it, typically if you get a negative number here or something kind of weird, it's probably in radians, okay? All right, so the next thing we're going to do, let's look at an example of how do we do this process, okay? So we have vector A as a magnitude of 15.3 at an angle of 58.4 degrees. Vector B as a magnitude of 26.9 at an angle of 15.1 degrees. What is A plus B, and then what is A minus B? So here we're going to add, and we do a second part where we subtract, okay? So the way I really learned this, so we're going to use our AX equals A cosine theta, AY equals A sine theta, right? First thing we need to do is break these vectors down. And so I just learned organization. Okay, I just find it's best if I organize myself into a small little chart here. Okay, and again, this comes about by how many vectors you have. So we only have 2 vectors, so I only need 2 rows, but the third row is going to be my answer. Okay, and you'll see we'll do an example how does physics use this, where we'll call like the resultant will be like the net force or the net acceleration or the net velocity. Okay, so I'm going to do A cosine theta, A sine theta for both, even though this is technically B. I mean, it's the same thing. This A really is just an arbitrary letter. I can call it anything I want. So I'm going to do 15.3 cosine 58.4, and I'm going to get 8.0. I'm going to round, and then I'm going to do 15.3 sine 58.4. I'm going to get 13. Again, I'm going to round. And then I do the same thing for vector B. So 26.9 cosine 15.1. I get 26. Again, rounding. And then 26.9 sine 15.1. I'm going to get 7. Right? So now I'm going to, since I'm doing A plus B, I'm going to add these, right? So it's like I'm going to put a little plus sign here. So plus, plus. And so it's going to give me an Rx value of 34, not 36. So it's going to be 34, and then 20. So now I can figure out what is the magnitude of r. So I'm going to do the square root of 34 squared plus 20 squared. Okay. So square root of 34 squared plus 20 squared gives me an answer of 39.4. Okay, and then I find the angle. I'm going to do the inverse tangent of my y value divided by my x value. Again, these are based on my components here. So the inverse of 20 divided by 34, inverse tangent, is going to give me an angle of 30.5 degrees. Okay, so so if I want to say A plus B equals 39.4 at an angle of 30.5 degrees. And that angle is measured from the horizontal. Okay. Now, subtraction, the only real difference is where we added here, we're going to subtract. So my box is my chart is pretty much the same. So I have x, y, I've got my components. I always draw this box differently, but it's fine. Okay, so these numbers are going to be the same because the first step would be to do a cosine and b, or a cosine, a sine. So regardless, if I'm using the same vectors, I'm going to get the same answer. So now the difference is going to be, I'm not going to add them, I'm going to subtract them. Okay, so I'm going to do a minus b. So 8 minus 26 is negative 18, which now tells me my answer is going to go to the left, right? And now this is going to determine if it's going to go up or down. And that's, so 13 minus 7 is 6, which means it's going to go up. So my resultant will look something like this, right? And now we just simply do our calculation. So r equals the square root of negative 18 squared plus 6 squared. So plus sign. And I go 18 squared plus 6 squared, square root of that. I get, we'll round it to 19. Okay, so this r would have a magnitude of 19. Now what would be the angle? So we're going to do inverse tangent, right, of our x over our y divided by our x. And it's going to be 19 at 18.4. Now this 18.4 is actually from negative x, right? And so if you put it in your calculator as you see here, you're going to get a negative 18.4. That just means that our negative ends up with our x, so we're going left, then up. So r, or what we call a, or what our answer or problem was, a minus b is going to be 19.0 at 18.4 degrees above negative x. Okay. In math, you probably find that this would be like 108.4 degrees if you want to say that. But in physics, we always measure from the vertical or from the horizontal, and we don't do those coterminal angles or whatever we call those, just because it's, you know, we're working simple, right? We're trying to make life simple on ourselves as physicists. Okay. Now, there's many times where you're going to have to scale up or down a vector. So to do so, you multiply the magnitude, right? So the scaling has to do with the magnitude. It has nothing to do with the direction, okay? So you're going to multiply the magnitude of the vector, but not the direction, by a scalar. Okay, so in fact, you see the kind of the start of the word scale there, okay? So this would just be like multiplying by like a number. So here we're going to have multiply the vector m, which is equal to 7, 3. So what this means is I've got an x component of 7. In fact, this would be not a, but m, because we name our vector here. Okay, so this would be like mx, my. And what you do is just simply multiply each component by 3. Okay, so if I do 3m, which is what I'm doing, I'm going to do 7 times 3 and then 3 times 3. Okay, so now my vector becomes 21 Okay. Now I know it looks like an ordered pair. Sometimes you'll see kind of these, you know, the what looks like greater than less than bracket. This is the more common way to write it. Okay. So what does that mean? My original was like this. So 7, 3. Now my new one is 21, 9. The thing that changes, right? So then if I draw my vectors, so notice that the magnitude changes, right? So the magnitude of M has changed. All right. Let me just get that because that notation we haven't talked about. You'll see that it got bigger, right? But the thing that did not change would be the angle, okay, the direction. Just the size got bigger, not the angle, okay? Now, how do we apply this to physics? So here's just an example. So here we're going to talk about net force. So we have Sam and Alex are pulling on a box. Sam pulls with a force of 200 newtons at an angle of 60 degrees, while Alex pulls with a force of 120 newtons at 45 degrees. And we're going to say this is below, right, negative x. So one's pulling up and to the right, one's pulling down and to the right. What is the net force acting on the box? So what we're going to do is we're going to add, and we'll call Sam S and Alex A. So we're going to add the force by Sam to the force of Alex, okay? And so if we just kind of write some of this, so Sam is 200 newtons at 60 degrees. Alex is 120 newtons at 45 degrees, but this is below negative x, or sorry, positive x. Be positive x here, okay? So if we just draw a quick picture, it's going to look like Sam, right, Alex. And we want to know the net force is kind of really what splits them in some way. I don't know what it's going to look like, but this will be my resultant, okay, that we've talked about before, okay? So again, we just apply what we talked about. So the first thing we're going to do is we're going to make a box or make our chart, right? Again, I always make this chart differently for some reason. So we got Sam, Alex, resultant, right? Or in fact, let's not call it resultant, let's call it F, right? Because that's what we're looking for. We're looking for the net force. So Fn. So if we do A cosine theta for Sam, so we're going to do 200 cosine 60. So it's 100. And then we're going to do 200 sine 60. It's 173. Okay. And then we're going to do 120 cosine 45. Now, the great thing about 45 is that it's the same. Okay. The difference is this is going to be positive. This one will be negative. All right. So now we add down because we're finding the net force. So we're going to add down. So 100 plus 85 is 185. And then 173 plus negative 85 is 88. Okay, so there's Fnx and Fny. Now how do we find Fn, or the magnitude of Fn? We're going to do the square root of 185 squared plus 88 squared. Okay. Now, does it make sense that it's more towards Sam's side? Yeah, he's pulling with more force with a bigger angle. Okay. So 185 squared plus 88 squared gives us a magnitude of 205 newtons. Okay. And now we find the angle. So we're going to do the inverse tangent, right, of y over x. So 88 over 185. The inverse tangent of 88 divided by 185, that's going to be 25 degrees. Okay, so what is the net force acting on this box? So, whoa, sorry. I don't know why all of a sudden I went that big. Let me advance, bring this down to, no, okay, bring that down to 1. I feel like I've gone all of a sudden to highlighter. Oh, I clicked pen too, that's why. All right, so all of a sudden I'm just flipping around over here. All right, so Fn will equal 205 newtons at 25 degrees. Okay, and then you could say above positive x, right? Because that's where it ultimately ends up being. All right. So that's just some base.